Greetings YouTubers, welcome to part 5 in the Backpacking Stove Efficiency series. And this episode takes the heat exchanger systems examined in part 4 and subjects them to the effects of wind. Each video in the series builds upon those introduced previously, so I do recommend you watch them in order. And key concepts already covered include how pot diameter and flame level relate to fuel efficiency, the effects of wind, and the benefit of screens. My methodology has been described in more detail, but for a quick review, all tests are conducted inside my climate-controlled shop using precision instruments and a digital fan that's calibrated by wind meter to the mile-per-hour settings used for testing. For each boil, I use a volume of 415 milliliters, and that's enough to make just about any backpacking meal, and it fits nicely in a half-liter pot. And by boil, I mean heated to 200 degrees, which is plenty for pasteurization, and it will make a hot drink or rehydrate freeze-dried food nicely. And for the flame levels, I have 3 different MSR low-down adapters, each one set to low, medium, or high. That way, every stove gets the exact same fuel rate regardless of how different their individual valves might be. And all of this allows me to have a margin of error that's on the order of hundredths of a gram of fuel. And that's sensitive enough to detect even relatively small effects. Now, on the subject of accuracy, I do need to mention that I had some problems during testing. I had equipment failure that caused me to lose the setting on my high flame standard. And after much anguish, I found the source and fixed it, but I can't say that I was able to get high back to exactly what it was before. I did my best, but there were challenges. I'll explain in more detail near the end of the video for those that may be interested, but just know that when comparing high flame results here to results shown in previous videos, there could be more discrepancy than with the medium and low settings, which were not affected. So in part 4, I introduced a series of HX systems made up of 2 components each, a vessel and a stove. And you'll see that video for details of the weights, sizes, and construction for each system, but as a reminder, I paired a fire maple kettle with the BRS 3000 stove. The heat exchanger ring is large enough for the stove to sit somewhat recessed under the kettle, hopefully providing some measure of wind resistance. And along those lines, I put a Petrel pot on top of a Soto Windmaster with the optional Triflex support. And this allows the stove arms to fit inside the Petrel's slots, snugging the burner tighter into the heat exchanger ring. Now, this was John from Flat Cat Gear's idea and is specifically intended to improve performance in the wind. And a lot of you asked about testing the Petrel sitting on top of the stove arms as well, so I also tested that here to see how the performance is affected when the air starts moving. And speaking of Flat Cat, another system tested is the Cheetah windscreen, outfitted on a fire maple stove with a wide C pot. And the last 3 systems all use vessels with manufacturer supplied burners. It's the Jetboil Stash, MicroMo, and the MSR Reactor. So at this point I should reiterate that I don't have any sponsorships at all. I buy all my own gear at regular price. I don't accept stuff for review or have affiliate links, coupon codes, or any kind of partnership with anybody for anything. Okay, all that out of the way, let's get to some testing. The procedure was to run each HX system through wind speeds of 1, 3, 5, and 7 miles per hour, and to do that at each of 3 flame levels, low, medium, and high. So starting with the kettle, here's what the data looks like using a low flame. In still air, the efficiency is excellent. The grams of fuel required to boil begins to rise even with the slightest movement, and when the breeze begins to pick up, fuel use more than doubles. And by now I can recognize this sharp jump as the approaching limit to the system. This arrangement of vessel and stove would not be able to boil at 5 miles per hour and above. So here's what the low flame looks like under the kettle at increasing wind speeds. Then you just repeat the series again, this time on medium flame. With a stronger flame to help overcome the blowing of the wind, you can now push the system all the way to 5 miles per hour. The efficiency is poor, but you will be able to boil eventually. And also note what happened elsewhere. From part 1, we know that a low flame is generally more efficient than a higher one. It may take longer to boil, but you waste less heat to the environment. But as we saw in part 2, wind can change that dynamic. And it's still true at 0 miles per hour. Low takes less fuel than medium, but look at the difference in performance at 3 miles per hour. On low, it took 11 grams of fuel to boil. And on medium, at the exact same wind speed, it only takes 7.31 grams. These charts don't just illustrate that turning your flame up can help save fuel in the wind, they also provide some guidance as to when and by how much. So let's take a look at the run on high, and then I'll show you how I put it all together. This is what I call an efficiency profile. It shows the different miles per hour using the flame level that was most efficient at that speed. So at a glance then, you can see how to operate this system depending on the wind. On a still day, low is the most frugal. As soon as there's any movement, turn up to medium. And when the breeze is strong, use high. And even with a strong flame, a setup like this just won't make it to 7 miles per hour. I did this analysis with every system. Now I'll move through all the graphs. Pause the video if you want more time to soak up the numbers. Next, take a look at the Jetboil stash. It was the efficiency champ from part 4, but it has a fairly unprotected burner, so the prediction is that it might experience trouble in the wind. It actually ended up being even less robust than the Kettle system, which used a notoriously susceptible BRS stove. And given that spike at 3 miles per hour, I didn't even do 5 miles per hour on low. The progression wasn't as steep on medium, so I gave 5 miles per hour a try. After 13 minutes it peaked and wasn't able to get above 160 degrees, registering a fail for that test. And the same was true even with a high flame. As it turns out, the most efficient flame level was medium regardless of wind speed. So far, we haven't yet seen a system that can handle a full 7 miles per hour. So let's take a look at the Cheetah, which is explicitly marketed as a windscreen. And it gets you to 5 miles per hour even with the weakest flame. On medium, we finally have results all the way up to 7 miles per hour. In fact, the Cheetah is doing 7 miles per hour significantly better than the Kettle does 5 miles per hour. Looking good. But this bump at 3 miles per hour caused me some consternation. It should be an ordered progression. More wind means more fuel, whether it's linear or exponential. My first thought was something went wrong with that test, so I ran it again. And sure enough, I got a similar result. So how could increasing the wind to 5 miles per hour make the system more efficient than at 3 miles per hour? Well, I think a better way to ask the question is, what's happening at 3 miles per hour that is spoiling the result? So watch and listen carefully to the medium flame at 1 mile per hour. That sounds pretty consistent. Now hear what happens at 3 miles per hour. Suddenly the flame is faltering significantly. It sputters continuously throughout the burn. Also, note just how much blue flame begins ejecting downward through the bottom of the windscreen. There was almost none of this at 1 miles per hour, and at 5 miles per hour and beyond, it is mostly gone again, coinciding with a return to better fuel efficiency. So this reminded me of a performance quirk with the Simmer Shield windscreen from part 3. So after an unexpected fuel increase with just a little bit of wind, I discovered that it actually worked better without the included floor. And at the time, I offered speculation about a possible Venturi effect creating suction through the relatively small holes in the bottom. So looking at the Cheetah, you can see it has more bottom cover than any other HX system tested, making it most like the Simmer Shield's problematic floor. I'm starting to suspect that depending on conditions, it can be possible to have too much protection on the bottom. So this counterintuitive performance bump reappeared with a high flame, actually lasting a bit longer and spilling into the efficiency for 5 miles per hour as well. Now here is the efficiency profile for the Cheetah. You keep a low flame all the way up to 3 miles per hour, and see how the bumps aren't there. It sort of exemplifies the value of looking at things this way. When used at its most efficient flame level for each wind speed, there's a nice progression as expected. So a lesson might be that if your stove starts sputtering in a particular condition, adjust the flame level to reestablish a steady burn. It can save you fuel even if that means actually turning the flame down in the face of a somewhat increased wind. You'll have to try to diagnose the cause, however. If the reason is your flame is simply being blown away, then turning it up is usually the more efficient response. So next up was the Petrel system. With the burner in there close and protected, I was able to get a boil on low all the way up to 7 miles per hour, though you can see from the spike that it's about as far as you'll get with a weak flame. It looks pretty good on medium. That tiny drop at 7 miles per hour is within the margin of error. On high, you can see how relatively unperturbed this system is, with only slight increases in fuel use from 3 to 5 and even 7 miles per hour. And that's the limit to what my fan can do, but there's reason to believe the Petrel would continue to reach a boil subjected to even stronger winds. The efficiency profile is pretty textbook. The steady progression of fuel use and an increase from low to medium to high flame as the speed increases. So from part 4, I made an observation regarding the relative fuel efficiency of the different HX systems tested. Despite a variety of pot and burner designs, there was a distinct correlation between the pot burner gap and the system's performance. Where the gap was large, fuel efficiency was better. And as the gap shrunk, the fuel required grew. So as always, correlation's not causation, but this led several people to ask me about testing the Petrel with the pot sitting on top the stove arms instead of slotted down into them. The Petrel, as tested, had the smallest gap and the worst efficiency with no wind. Well, they say the gold standard for a theory is its predictive power. The prediction here would be that increasing that gap by setting the stove on top would improve its performance, at least at 0 miles per hour. Because I crave to please, I tried it out. On the low, the higher seat did, in fact, beat the performance of the closer fit, as predicted. A countervailing effect of this unprotected stance, however, is that performance will begin to suffer as the air starts moving. So I tried getting a boil at 3 miles per hour, but couldn't do it. For direct comparison, here's a back-to-back look at the flame shots of the Petrel on low at 3 miles per hour. First slotted in low where the performance is still reasonably good, and then sitting high where it can no longer achieve a boil. So I also tested the alternate arrangement on medium. And again on high. And this then is the revised efficiency profile for the Petrel, combining the most fuel-efficient options from high and low mounting. The lighter shade is for the top sitting arrangement. As you can see, it was only in no wind that being on top of the stove arms was a benefit. The moment air begins to flow, the more protected setup has the advantage. You have the option to adjust it in the field for optimum efficiency depending on conditions, and because no extra equipment is required, the adaptability costs you nothing in additional weight carried. So moving on, the Jetboil MicroMo was second only to the Stash in static fuel efficiency from Part 4. It was also one of the few to make it all the way up to 7 miles per hour with just a low flame. Also looking very good on medium. And the performance on high. So putting that together in an efficiency profile, you can see that at least in the range tested, you never need to go to high flame for optimum efficiency. And lastly, we have the MSR Reactor, a very different design from all the others, easily the heaviest, but also marketed as the wind-resistant champ. On low, a nice smooth progression in the face of increasing wind. With a medium flame, the progression is even flatter, with almost no increases in fuel use required for 7 miles per hour versus 5 and 3. And the results when the flame is set to high. Assembled into an efficiency profile, we see that low is the best in still conditions. Otherwise, you're better off on medium all the way up to 7 miles per hour. No flame shots for the reactor since it's all covered up and there's nothing you can see. Okay, let's look at how the individual stoves perform. If you own one of these, it's sort of a guide on how to use it most efficiently depending on conditions. But what if you're trying to choose between them? Which one works best? As always, there's no simple answer to that question. It depends. Consider for the moment only fuel efficiency. We'll talk about weight later. We can begin comparing the systems to each other. To that end, I created a series of efficiency rankings beginning on low flame at 0 miles per hour. So within the margin of error, the Stash, MicroMo, and Kettle systems are all essentially tied for first place, with the Cheetah very close behind. The reactor is a ways behind them, and the Petrel was last. This is what was seen in Part 4. Now see what happens when you start moving the air. The Stash slips slightly compared to the MicroMo. Its open design doesn't cover the flame as well. The Kettle and the Cheetah slip even further. The reactor and the Petrel keep their spots in the back, and the whole vertical spread of the chart expands. 1 measly mile per hour wind isn't much of a change though. Check out what happens at 3 miles per hour. The MicroMo's still in first, with the Cheetah close behind. Now though, the reactor and Petrel have moved forward to the middle of the pack. The Kettle and Stash, two of the first place systems in still air, have fallen not just into last place, but are now using almost double the fuel of the MicroMo. And at 5 miles per hour, it changes even further. The former top performers now fail to even reach target temperature, and the erstwhile last place couple are now in first and second. The whole ranking system has reversed itself. At 7 miles per hour, only 3 systems are still able to cross the finish line at all, regardless of time. And that was all just at a low flame, though. This evolution of the efficiency rankings can be observed for medium as well. And as you watch, with some differences, the basic pattern of changing rank unfolds similarly. And again, the situation remains recognizable with a high flame. In stronger winds, a Kettle, sitting atop the humble and notoriously susceptible BRS stove, consistently outperforms the Jetboil stash, until we get to 7 miles per hour, where despite the stronger flame, only 4 systems remain viable. Now remember that not all systems reach peak efficiency at the same wind speed for any given flame level. And that means I'm gonna slap you with one more series of charts, the efficiency rankings of the efficiency profiles. Never ceases to amaze me that some people actually watch the whole video. Anyway, here's an efficiency ranking at 0 miles per hour using the most efficient flame level for each system in no wind. Right from the start, the stash works best on medium. The rule, though, for no wind is a low flame. And remember that the Petrel prefers to sit on top when things are still. With even a little bit of breeze, most systems are ready for a medium flame. And as the wind picks up to 3 miles per hour, only the Cheetah still works best on low. And it is, after all, a dedicated windscreen option. At 5 miles per hour, the Kettle needs a high flame just to stay in business. The Petrel also prefers high versus the Cheetah, with similar performance that's still happiest on medium. Not to be missed, however, is the famous Reactor is only in second place, even with a relatively strong breeze. At both 3 and 5 miles per hour, it's the MicroMo that sips the least fuel to boil a single batch of water. It is only at the strongest 7 mile per hour wind did the heaviest system finally come to the front. So far, this has all been from the strict perspective of fuel efficiency. Even with just that singular priority, the answer of which system is best still depends. Weather obviously is uncertain, and you can't be sure what wind speeds you'll encounter on trail. And the longer you hike, the likelier it becomes that you'll experience a broader range of conditions. You're here presumably because you are interested in wind performance. So let's look at only the 4 systems that survived to 7 miles per hour and consider their average fuel efficiency across all wind speeds tested. And as it turns out, the MicroMo wins by about half a gram of fuel per boil over the Reactor, which was the nearest competition. True, that's not a huge amount, but it is enough to get you 1 extra boil out of a small gas canister. And since the MicroMo is also lighter than the Reactor, it makes this an easier elimination. The Cheetah and the Petrel might require a bit more fuel, but they're both substantially lighter systems than the MicroMo. And that means we finally have to open up this can of worms. Combining fuel efficiency with an appreciation for weight efficiency is the last step in this analysis. So for the big picture, we need to compare these heat exchanger results to those of the conventional pots outfitted with windscreens. So here then is an efficiency ranking combining both kinds of systems. The HX setups are shown in darker shades with the conventionals of paler hue. For reference, a bare BRS is also shown. With no wind, you can see the basic pattern. The heat exchangers are, for the most part, more fuel efficient than a regular pot. No real surprise there, windscreens don't do much for you when there's no wind. Add a 1 mile per hour breeze and things look mostly the same, though the unshielded BRS quickly drops behind. At 3 miles per hour, the sorting goes absolute. All the HX systems outperform any of the screened pots. And at 5 miles per hour, we lose the stash and BRS entirely, and the Kettle slips away from the HX crowd. And by 7 miles per hour, these are the only systems left that can still bring a boil. As shown, the separation between types has only gotten wider. So in fairness, 2 of the most open HX systems were eliminated entirely at this wind speed, but of those that remain, there's a substantial difference between the average fuel efficiencies from each group. And I confess that I did not expect the difference to be this pronounced. And before getting into the weight efficiency calculations, I want to point out that the grams of fuel conserved are not the only way to evaluate the worth of a fuel efficient system. For some, it may well be the number of boils achievable from a given canister of gas. And if, for whatever reason, supply is limited, just how much you can get out of your very last fuel tank might end up being the top priority. So, here's how these fuel efficiency numbers translate into boils per can. The MicroMo will literally get you twice as many boils per container as an Ocelot Mini. Depending on your needs, that alone could be what drives your decision. And that being said, the MicroMo is the second heaviest system shown, and the Mini is almost the lightest. So it remains to be seen then whether the added mass of the MicroMo's bulky and proprietary pot burner system ends up being worth its weight in fuel savings. To put the weight differences in perspective, here they all are side by side. So the Ocelot Mini is down here. And that's 107 grams for everything, the pot, a lid, burner, and the windscreen. In contrast, the MicroMo system is way over here at 315 grams, a weight difference of 208 grams. Well, that's essentially the gross weight of an entire extra small canister of gas, which you would have to carry with the Mini because it would require twice as much fuel. Weight-wise then, it's basically a wash between carrying this and this. However, there's a lighter way to carry this much fuel in one of these. A medium can has a little more fuel than two small ones, but it weighs only 374 grams, which is a 48 gram savings over carrying both of these. So what you'd actually be comparing is 481 grams versus 526. So amazingly enough, despite requiring twice as much fuel, the Ocelot Mini is so much lighter than a MicroMo that it remains the most weight efficient option, at least up to a 2-can scenario. You all can argue as much as you like in the comments section about whether saving 45 grams is worth doubling your fuel costs. To put that in perspective for the people who cut the tags off clothes to save weight, that's the equivalent of 169 tags. For years I've been saving these things, just waiting for the opportunity to drop that rock. But seriously, folks, as always, I view my role as simply providing information. The value judgments have to be yours. It is surprising, though, to see just how hard it is for fuel efficiency to overcome additional system weight. Now, as I've pointed out in the analyses from previous videos in this series, these weight calculations can come with a lot of caveats. For starters, how many boils per day do you require? How many people in your party will you be cooking for? And how many days will you be out? And that all combines into a single number for the total number of boils you'll require that trip. And then you'll need to choose which two stove systems you'll be comparing against each other, and what is their total system weight difference, as well as the difference in their fuel efficiency. Now you're in a position to calculate how many boils a heavier but more efficient system will have to perform before it makes up for its own weight. Just compare that makeup number to the number of boils needed for your trip, and you can see if circumstances will allow the heavier stove to become worth its weight. Sounds like a pain, I know. I'll show you an example, but I also made you a calculator to help. It can be found on its own tab in the free downloadable spreadsheet linked in the description box below. All the data and the graphs from every video in the series can be found in that one file. So using a calculator is as simple as I can make it. You only fill in the 5 colored boxes shown. We'll start with the fuel weight, not the gross weight, of the canister desired. See the little chart with the 3 standard can sizes for reference. And you can put in any other number should you be using cans of a different capacity. So for this comparison, I chose the Ocelot Mini versus the MSR Reactor using their relative grams per boil performance at 7 miles per hour, where the difference in efficiency is greatest. The computation fields will populate automatically. And what this shows you is that stove 1 is 283 grams lighter than stove 2. Stove 1 also requires 7.37 grams more fuel per boil at the speed chosen, and that means stove 1 gets 9 less boils per can if using the small size. And lastly, it shows you that you would need at least 38 boils with stove 2 before the fuel savings from efficiency finally make up for the extra system weight. So if your total number of trip boils required is less than 38, stove 2 won't be worth the wait. Simple as that. As far as strictly weight carried on that trip goes, look only at short trips and small cans, or plan an expedition set up for a group. Not worried about 7 miles per hour? Use the data for 3 miles per hour or 0. Prefer to compare a bare BRS and Tokes pot with a Jetboil? Suit yourself. With both the data and the calculator, this hopefully empowers you to make as many different comparisons as you want. One more example just because. Let's compare the Ocelot Mini to a Petrel at 7 miles per hour. The Petrel still has pretty good performance, but it's lighter than either the Reactor or a MicroMo. It appears to be a better compromise. Though it still takes 21 boils to make up for the extra weight, and there aren't that many in a small canister. Okay, before I get into the summary, I'll go over what happened with the equipment failure that I mentioned earlier. I think it makes a good tale about trying to observe the scientific method while conducting tests such as these. To make a very long story as short as possible, while testing I realized that my boil times on high were actually taking longer than those on medium. Now, the fuel efficiency may go up or down with a stronger flame depending on conditions, but boil times for a faster flame have always been quicker. So it appeared that one of my flame standards was off. So, not knowing for sure whether it was my medium or the high, I ran checks at both flame levels with 2 different stoves to compare with my historical results. So for the stash on medium at 0 miles per hour, I originally had 417 grams per boil. And this time I got 4.2 grams. Only 0.03 of a gram difference. Not bad. And for a bare BRS with a Tokes 550, I had 7.13 grams before and 7.21 grams now. Still only hundredths of a gram difference. Way back when, the BRS Tokes spent 9.24 grams boiling on high. And this time, it only cost 7.71 grams. Well, there's your problem. Somehow, my high standard was acting more like a medium. Now, after setting each of these regulators, I took the handles off to avoid the possibility of the valve ever getting bumped. And when moving them, I carry these things around like a heart for transplant and store them each in their own drawer with no other objects inside. I've been very worried about it and very careful, so this development was disheartening. Before touching my regulator, I ran more tests using 2 different stoves and 2 different gas canisters to make sure it wasn't some failure on those ends of the equipment chain. That left the extension hose I use to run from the can into the regulator. It's necessary for the additional valve. It occurred to me that something might have worn out or gotten clogged, thereby choking off the supply and preventing high from being high enough. Well, luckily I had a spare, but regardless of which hose I chose, the problem persisted. Finally, I gave in, and I decided I would have to try and readjust the valve on my high standard. And it didn't work. No matter how far I turned, even opened all the way, I couldn't get the boils to go faster. Something else was limiting the fuel flow. But there aren't any more pieces left. I'd used 2 different stoves, 2 different hoses, 2 different gas canisters. That should eliminate those parts of the chain as suspects. Unless, what if I was to be so profoundly unlucky as to have had the simultaneous failure of both elements in a part of the chain? It was only then that it occurred to me that this is the first time I had ever used refilled canisters for testing. By now I've assembled a small army of almost empty cans. You stop using them when they get too low or the numbers will be off. So to make use of all the leftovers, I used an adapter and was able to combine enough partials into 2 full recyclers. So I ran some more tests using a brand new can. Sure enough, high was high again. It appears that the refilling process somehow damages, misaligns, or otherwise affects the Lindel valve on the canister itself. It causes some kind of obstruction or restriction that reduces the max flow. Nothing would show up at low or medium because the canister can still produce that rate. But an unseen cap on flow renders high not what it used to be. An interesting but painful lesson because it means that I turned my high regulator from its original setting for no reason. I know what you're thinking. Just adjust it back to what it was. Well, easier said than done. These things aren't built for fine adjustments or accuracy and repeatability. Originally, I set high to be just low enough that it wouldn't max out any of my stoves to guarantee that everybody would be passing the same amount of gas. I didn't have to try and match it to anything. In short, I spent days and days doing many tests and simply cannot get it back to what it was before. The best way I can describe trying to work with this cursed valve is by likening it to like a rubbery interface, probably due to the seal inside. So when attempting fine adjustments, it gives before moving and then unsticks and launches forward more than intended, making it impossible to simply increment slowly until set. And aggravating all of this is the fact that the valve's highly sensitive in this range. Tiny rotations have big consequences. To make matters worse, there also appears to be creep. After an adjustment, the results will continue to change over the next several tests as the apparent friction in the system slowly gives way over time. So put all that together and it becomes an extremely frustrating situation of constantly over or undershooting the target. So if you compare Part 4's results on high at 0 miles per hour to these new ones, there's a difference of up to half a gram of fuel. And none of this means the comparisons within this video aren't valid, and low and medium weren't affected at all. It just means that trying to compare this video's results on high with previous data will come with a greater margin of error than usual. And all of this could have been avoided if I had just diagnosed the problem correctly in the first place and not touched my high standard. For that, I apologize. Going forward, if there's a direct need to compare data across videos, I will just have to retest all of the high stuff to keep it consistent. And that's what I did here with the data for 0 miles per hour. Okay, time for the summary. Heat exchanger systems are built for fuel efficiency, but their performance in wind can vary widely. At rest, they are somewhat similar, but as the wind speed increases, the differences grow. And by 7 miles per hour, only 4 of the original 6 systems are still able to reach a boil. The stash, for instance, went from best to worst, failing even before a BRS Kettle system. So putting that into perspective with the conventional pot and windscreen systems from Part 3, it's clear that even at 7 miles per hour, the HX systems rule the efficiency rankings. And that can translate into literally double the number of boils per canister. Still, all that performance comes at a substantial weight penalty, with screened pot systems being universally lighter than heat exchangers. If pack weight is your priority, it is actually lighter to carry this setup, bringing twice as much fuel, than it is to carry the efficiency champ. This depends, of course, on how many boils and therefore how many canisters your trip will require you to carry at the same time. Given the regularity of resupply, even through hikers may never need to carry enough fuel all at once to make up for the weight penalties of HX systems. The longer expeditions may indeed be able to reach the point of positive returns. So to help you figure out those particulars for your own adventures, I put a calculator in the downloadable spreadsheet. Fill in the colored fields with the data for any 2 stove systems at a particular wind speed. The calculator will show you the number of boils you'd need to perform before a heavier but more efficient system can become worth its weight. Of course, if fuel is in short supply for some reason, efficiency may trump weight as your top priority. The data is provided not to tell you which stove is best, because there isn't one answer to that question for all circumstances. It's there to help you make informed decisions for yourself. For those that have asked, I do have plans to test materials for relative efficiency. I'm assembling a collection of similar pots in aluminum, titanium, and stainless steel, just to see if that makes a substantial difference in fuel use. Also, there are some interesting options combining HX pots with external windscreens. Flat keg here makes this ring to protect the stash's very vulnerable flame. There are other products and also ways I might try to get crafty myself, so stay tuned for those results. It would be nice to see how low we can push the weight efficiency barrier. And as always, I very much appreciate your time, and thanks for watching.